So quantum electrodynamics is not a easy breezy thing. So it holds its, privilege to be the most accurate one, because it gave many accurate predictions and accurate description of the fundamental interactions. Quantum electrodynamics was originally presented and put forwarded for the first time by Paul Dirac in 1928, when he combined quantum mechanics, electromagnetic theory, and the special theory of relativity to describe how electromagnetic particles interact with each other. And these electromagnetic particles, that everything that has electrical charge on it, and even the photons, because they are electromagnetic waves, so nothing is left behind. Everything positively charged or negatively charged. We study all of them in one place. So it was originally really complex. It has many complex calculations, and it's really tough to visualize that how the particles are interacting with each other. Later on, Richard Feynman presented a formulation, new ideas, and methods in quantum electrodynamics, for which he was awarded a Nobel Prize in 1965, along with other scientists as well, like Julian Schwinger and the other one. I'll mention their names. So they presented their methods, which were really easy. And out of them all, Richard Feynman's method was the simplest one. And it's even used today. If you know the word Feynman diagrams, we have these Feynman diagrams that we generate based on those Feynman rules. These Feynman rules helps us to draw the Feynman diagrams, and Feynman diagrams are actually the visual representation, the pictorial representation of those interactions that happen between the particles. And from that single diagram, we can find out an expression for the amplitude of the interaction. Okay. And without this, okay, if we don't have that Feynman diagram in mind and we are doing it from the conventional method, the process to write down the amplitude is really tough. We'll see in S matrices. I'm not doing the S matrices topic first because it is a bit different and difficult, and I'm doing it first because so that you have that thing in mind, that yeah, Feynman diagram is coming and we will be following it. So S matrices is actually, we should know about it, but we'll see that how difficult those methods are and how easy the Feynman rules have made that calculation in quantum electrodynamics. Okay, so Feynman rules and Feynman diagrams holds a special place in this theory and in understanding this theory. And most of the students are learned because they make the complex calculation way easier. So that's a kind of tool that we use for the calculations in quantum electrodynamics. All right, I hope that's clear to you that how quantum electrodynamics and Feynman rules are related to each other. Feynman presented his own contributions, which were also presented by other scientists. So they were all given the Nobel Prize because they did an independent work. But Feynman rules were the easiest one. Okay, he was a great teacher and one of my role model. So we'll be studying the Feynman rules in this video. All right, and as I told you people, what is Feynman rules used for? Feynman rules are actually the set of rules, the set of steps that we follow to draw the Feynman diagrams. And those Feynman diagrams are actually the pictorial representation of the fundamental interactions between the particles. And following those rules, we can find out an expression for the amplitude of the fundamental interactions under consideration. Let's quickly get started with Feynman rules. And first of all, we'll write some preliminary things so that we form the foundation of our discussion. And then we'll write down the rules, because we can't just directly jump into the main thing. We just have to establish the scene first. Okay, set up the scene, and then we can have the discussion based on that scene. So let's write it down. Feynman rules, or key tools to determine the amplitude of interactions between the fundamental particles with convenience. All right, so using the Feynman rules, we can easily determine the amplitude of interaction between the fundamental particles. Okay, whenever we have all these fundamental particles and their interactions, their different kinds of interaction are resulting whatever we are seeing on the macroscopic world as well. So we want to study and understand what kind of interactions is happening between those fundamental particles, and we want to formulate the mathematical basis of those interactions. So Feynman rules helps us to determine that mathematical basis, one of the most difficult expression, which is the scattering or the interaction amplitude. We can determine the interaction amplitude really easily using the really quick and easy Feynman rules. Okay, we'll see they are really simple, and hence Feynman rules are the key tools. We use this tool to determine those mathematical stuff really quick and easily. We construct the interaction amplitude which we represent by m, okay, or something like that. We represent the interaction amplitude by m. We construct the interaction amplitude expression from Feynman diagram. Feynman diagram, what is Feynman diagram? It is the visual representation, visual representation of the interaction between the particles. All right, so we can see here so far that Feynman rules, we can use them to construct the amplitude of interaction between the fundamental particles, but exactly how? So Feynman rules are primarily reliant on the Feynman diagrams for the determination of that expression. Okay, so in Feynman rules we have the most important component, which is Feynman diagrams. These Feynman diagrams are actually the visual representation of interaction between the particles. Feynman diagrams are actually really vital in the whole process of determining the interaction amplitude, and it's a part of Feynman rules. Okay, we'll see it. It's not different from Feynman rules. It's actually a vital part of it, and we construct the whole basis based on these Feynman diagrams. So let's see the symbols and notations that we will be following, and it will help us understand the whole thing that's going to happen later on. And understanding it beforehand is really a wise thing to do. So here I'll be writing for electrons. I can represent electron by E minus, I can represent positron by E plus. Okay, we can represent photons by gamma sign. Okay, you can also write here electrons, positrons, and here we have photons. In interaction we have three different things. Okay, we have the incoming particles. Let's say we have these incoming particles, they interact with each other here some way. Okay, we don't know how they interacted, so it's just the area of interaction, they interacted with each other. And then we have the outgoing particles. Okay, we can see here that we have incoming particles, outgoing particles, and the interaction section. We are interested in here the notations for the ingoing and outgoing particles. So we have an expression, a symbol and notation for incoming particles, okay, and then for outgoing particles. Here we'll write everything for incoming situation, and here we'll write for the outgoing situation. By incoming means the particles haven't interacted yet. By outgoing means they have interacted and now they are just going. Okay, so that is before interaction and this is after interaction. So if we have a electron which is incoming electron, okay, So we represent the wave function of incoming electron by symbol U. Okay, we represent it by symbol U, and we have positron. The incoming positron will be represented by symbol V, but a bar on it. Because electron is a particle and positron is the antiparticle, that is why we'll have everything opposite to each other. Like electron and positron will have opposite representation for everything. It's incoming U, V bar for incoming. And you'll see for outgoing electron we use U bar, and for outgoing positron we use V, because they have different wave functions because they are different particles. Okay, that is why we are using U as for the wave function of electron and V for the wave function of positron, but we have this representation to show that they are antiparticle of each other. Okay, so U for incoming electron and U bar for outgoing electron and opposite for the positrons. All right, for gamma, which are photons, if they are incoming photons, we'll use epsilon with mu in its subscript for incoming photons. For outgoing photons, which are outgoing, we'll represent it by E mu, which is epsilon mu and a star over it to show that it's the outgoing photon. These representations are really crucial because they'll be utilized in writing down the expression for interaction amplitude, and they'll be also used in the Feynman diagram. So you have to understand you have to understand it. Okay, I hope you are clear till that point. Now next on, what I'm gonna do is to draw their visual representations. Like if there is incoming electron, we use the straight lines to represent particles. Okay, straight lines. So if it is incoming electron, we'll write the vertex here, and the particle will approach the vertex. Approach the vertex means it is going towards the vertex. Vertex is actually a point where interaction happens. Since it's an incoming electron and it hasn't interacted yet, so the vertex will be ahead and the electron will be approaching the vertex. All right, and here for positrons, write down the vertex here. Okay, write down the line. Since positrons are the antiparticle of electron, the arrow will be opposite to that of electron. Okay, and that doesn't mean that the positron has interacted and it's moving away. These arrows doesn't show that where the particle is moving. Okay, they doesn't tell you that particle is moving in this direction or in this direction. They are just the representation to show that they are incoming electron or positrons. To differentiate positron from its antiparticle, we are using this opposite representation. Okay, that will be clear to you people later on as well. I'll make it crystal clear that what these arrows are telling us. So for now, you should know that write down the thing based on the intuitive knowledge that we have for the particle region, and for antiparticle we'll use the opposite of it. Okay, so we can see the vertex is here and the electron will approach the vertex. Now since if it's outgoing particle, what will happen is that the vertex will be here, since the particle has interacted, and it will move away from the vertex because it has already interacted and now it's outgoing particle. So vertex will come first and then the particle is going. And for positron, you'll use the opposite of it. Write down the vertex first, write down that line first, and the arrow would be opposite, which is this. Okay, so you will decide what the direction of arrow would be based on its arrow for the corresponding electron. For outgoing positron, you will see what the outgoing electron would look like and you'll draw the opposite of it. Okay, so that is how you'll do that. For photons, we'll use these curly lines to represent photons. We use these straight lines to represent particles, while we use these lines to show photons. So if it is incoming photon, so the vertex will be here and the photon will approach that vertex, and if it's outgoing photon, the vertex would come first, and it's moving away from the vertex like that. That's the representation or symbol and notation for electron, positron, and photons. You must be wondering that why I'm not writing it for all the particles in the standard model of physics. That's not needed. We need to understand the basis of rules, and we can use one set of particles, one set of particle, its antiparticle, and the photon. Okay, that's all we need. We don't need to study each and everything to understand the rules. Okay, only one set will be enough to understand the rules. So we'll be considering electron, positrons, and photons to understand the Feynman rules, and we'll proceed with it. So I hope you now understand the wave functions and what are the representations. Now let's see the Feynman rule. The first Feynman rule. The first Feynman rule is to draw the Feynman diagram for the process you are interested in. Okay, for example, you want to understand the interaction between electron and positron. So the first thing that you are supposed to do is to draw the Feynman diagram for those interactions. Okay, so that's the first thing that you are supposed to do. For a particular process of interest, if you understand the Feynman diagrams, you have done the whole thing. Okay, drawing the Feynman diagram the accurate way and understanding what's happening at each vertex and how the interaction is going on, that's really critical and important to understand. Okay, so draw a Feynman diagram with, now a new thing is coming here, with a minimum number of vertices. For a particular process of interest, okay, the process you are interested in, draw a Feynman diagram which has the minimum number of vertices. We'll understand it. Let me complete this line, and then we'll understand that what does that mean. According to Feynman ideas, processes with minimum number of vertices are more probable than the processes with relatively greater vertices. The two vertex process has the greatest probability to occur. The three vertex process is 100 times less probable than two vertex process. The four vertex process is 100 times roughly 100 times less probable than three vertex process, and so on. Okay, the probability keeps on decreasing with a greater factor than it was before. So the two vertex processes are of greatest probability, and hence the processes with least number of vertices are more significantly contributing towards the interaction amplitude than the higher vertices processes. Okay, let's understand what does vertex mean, what does two vertex process means, and why it matters. We need to understand it. Okay, because that is critical to understand. Then we'll proceed with it. don't be confused, we'll understand it right away and it will be crystal clear to you people. So what does the two vertex process mean? And we can't have a one vertex process. That is not um, feasible. That is not a physical process, and it uh, it doesn't conserve momentum, energy, and all that stuff. Okay, so the one vertex process doesn't occur. The least number of vertices that we can have is two vertices. So if we study a interaction between, let's say, electron and positron, okay, what happens is that one of the process, I'm telling you, one of the possibility that how the interaction could occur is that the incoming electron is here, it will emit a virtual photon. Okay, so it after emitting the virtual photon, the electron will move away with a changed momentum. It will have a different momentum. In here it was p1, here it emitted a photon and its momentum changed. Now this virtual photon is unstable and it will be absorbed by some other particle, which is, let's say, a positron. Okay, the positron absorbs this virtual photon at some other position, and after absorbing the virtual photon, the momentum of positron changed and it moved away with, this direction. You can see there are two points where the interaction is happening. At this point, you can see here the emission of virtual particle happened. Okay, at this vertex, this is vertex A. At vertex A, emission occurred. At vertex B, absorption occurred. And according to quantum electrodynamics, we can see and understand that all the interactions that happens are through virtual particles. Okay, virtual particle has to be emitted and virtual particle has to be absorbed in order to conserve energy and momentum and for the interaction to occur. Okay, hence emission and absorption are compulsory things that has to be happened, and hence there should be at least two vertices in each process. Okay, one vertex for the emission part and another vertex for the absorption part of virtual particle that is being shared. This is the two vertex process, and that is the simplest interaction that can happen. And if we see that there are the many things, there are the many ways the interaction could happen. For example, there is this electron and it emitted a virtual photon, let's say. Okay, now this virtual photon can turn into a pair production, like it can uh, change into a electron positron pair, which are virtual particles, which maybe at some point again combine to form a photon. And there are, endless possibilities that can happen in each kind of interaction, like between electron and positron. It can happen that this electron is captured by a positron and they turn into a photon, or like there are endless possibilities, and they give rise to greater number of vertices. Okay, this is the simplest, and there are endless possibilities in which multiple interactions could happen. Okay, so there could be a processes with three vertices. We'll see them later on. There are processes with four vertices, 4 points of interaction. There are vertices with there are processes with five vertices, six, and so on. Okay, so which processes, since we want to study the interaction between electron and positron, okay, so we want to know that we can't incorporate all these endless possibilities into the interaction amplitude, because that's complicated and that's not something convenient. So we are looking for the terms for the processes which are significant and vital towards the interaction amplitude. And Feynman told us that actually the processes with least number of vertices are contributing more towards the scattering amplitude or interaction amplitude. Okay, so for now we'll be considering only the least possibility of interaction, which is the two vertex process. We can include the higher vertex processes as well to increase the accuracy of the result that we are getting, but this is significant term. Okay, taking it alone would be enough to know much about the process or interaction that is happening and everything about it. Okay, since the other are least probable, they are contributing very, very tiny beanie less towards the scattering amplitude, hence they could be neglected and the two vertex process could be included. All right, so I hope you are clear that what's happening, and we'll draw the Feynman diagram. We'll see the two vertex process, and for two vertex process there is a possibility that this process can occur in another way, but it will also have two vertices in that way as well. So we'll consider both of these processes. We are supposed to include all the possibilities, all the possible interaction electron and positron could have with each other in order to get the scattering amplitude. Okay, because exactly 100% for 100% we don't know what's actually happening between them. Okay, we can never know that. So we have to incorporate all the possible kind of interaction they could have with each other, and they can have this outgoing situation. Okay, and in the meanwhile situation where they are interacting, there are endless possibilities in which they can interact with each other, and by rule in scattering amplitude we have to consider all those possibilities. Okay, and since for convenience and we know that the significant term is this, so we'll consider all the possible interactions that can occur through two vertex process. Okay, we'll see that this process have two possible two vertex processes. We'll draw them right now. So I hope that's clear to you people. Now let's read it again. For a particular process, we have to draw a Feynman diagram which has minimum number of vertices. Okay, we can see here that the interaction that we are going to study has two vertices. So we'll draw the two vertex process. According to Feynman's ideas, processes with minimum number of vertices are more probable than the processes with relatively greater vertices. The two vertex processes has the greatest probability to occur. The three vertex process is 100 times less probable than two vertex process. The four vertex process is 100 times less probable than the three vertex process, and so on. So the probability keeps on decreasing. Hence, the minimum vertex processes contributes more towards the scattering amplitude. Processes or interactions contributes significantly or primarily to the scattering amplitude, or you can say the interaction amplitude as well. Interaction is a better word. All right, so now we are studying interaction between electron and positron. Okay, electron and positron are interacting with each other through virtual photon or whatever. We have electron and positron back. All right, so this is the interaction that we want to study. Now let's draw the Feynman diagram for this interaction and see that how we are supposed to draw the Feynman diagram when we have a particular process of interest. This is the process of interest. We want to study the interaction between electron and positron, the electromagnetic interaction between electron and positrons. Let's draw the first possible Feynman diagram for this interaction. And as we see earlier, I told you that we have that incoming electron. Here is the vertex. At this position, it emitted a virtual photon. This is a virtual photon. And then after emitting it, the electron goes away and its momentum changed. This incoming electron has a different momentum. This outgoing electron has a different momentum. Okay, because electron emitted a virtual photon which changed its momentum, and the electron moved away with a different momentum now. So this is the half vertex process, and now we have that incoming positron. We have this incoming positron now, and it will absorb that virtual photon at this position. Since it's incoming positron, will use opposite sign, opposite arrow. It will be like that, E plus in. You can write it like that. This is in, this is out, E out and E plus in, and it will move away, and the arrow would be opposite to that of electron. Okay, and they should be such that they for example, it's a positron, so the outgoing and incoming arrows should align with each other, like in similar direction. It could be such that. Okay, that's another hint to see whether in which direction you are supposed to write the arrow. So it will move like that in opposite direction, while the electron will move in a conventional way, that we know that how the incoming electron will be like that and outgoing will be like that. But since it's a positron, we will invert everything about it, so the arrows will be inverted. It's E plus outgoing. All right, now we have this vertex A. This is the emission vertex, and this is the vertex B. This is the absorption vertex. All right, and we can see here one of the possible process. Now let's write down the wave functions and momentums for each of these expressions. This is incoming electron, its wave function will be u. Okay, this is outgoing electron, its wave function will be u bar. This is incoming positron, its wave function is v bar, opposite. Okay, and it is v for the outgoing positron. Now here we can see that this incoming electron and outgoing electron, their wave functions are all different, and we can use the numbers. Like this is u of 1, that shows that this is the wave function for the first particle, and this is electron. And similarly we can use v bar of 2 to show that this is for the positron, and then this electron u bar of 3 and v of 4 for the fourth particle. Okay, to show there are actually 4 number of particles that are involved in the process. Okay, so that just makes it convenient to refer to the particle like this is the first particle, third particle, fourth and second, and there are a total of 4 particles. And other than that, we'll see in the second rule, the second Feynman rule is to draw the momentum, label the momentum for each of these particles. So for that purpose we'll use p1 for the momentum of first particle, p2 for the momentum of second particle, p3 for the momentum of third particle, and p4 for the momentum of fourth particle. Well, this is all we need to label in this Feynman diagram, and this first Feynman diagram is completed. I'll call it as figure number 1. Now let's see another possibility and another type of interaction that can happen between electron and positron, and that is also a 2 vertex process. So let's do that as well. This is a horizontal Feynman diagram, and that another diagram that I'm gonna draw, you'll see it would be a vertical one. So what will happen is here is that we have that incoming electron and we have that incoming positron. Okay, and they will annihilate with each other. There is another possibility that electron and positron annihilate with each other. So this is incoming electron, so its sign will be like that, incoming positron like that. They will annihilate with each other at this point and turn into a virtual photon. Okay, so annihilation is happening in here. They turned into a virtual photon, and virtual photon, since it's unstable, it will quickly, depending upon its lifetime, decay into electron positron pair again. So it's outgoing electron and this is outgoing positron, sign opposite. So that is how another type of interaction could happen. You can see this is a vertical, this is a horizontal Feynman diagram, and this is a vertical Feynman diagram. And what happened in here is that electron positron, they interacted, they annihilated into a virtual photon, which after its lifetime decayed into electron positron pair again. So they are outgoing now, these are in. And this is another kind of interaction that could happen between electron and positron. We can see the diagram is almost the same. You can see electron positron, center is photon, then electron positron again. So we can see here that it's almost the same, but the process is different. Okay, and these Feynman diagrams, understanding them is really crucial. As we can see here, that this horizontal representation shows that this incoming electron emitted that virtual photon and it moved away. Then after some point, it's like they also represented that this is x1 position. The electron emitted the photon, virtual photon, at x1 position, and it was absorbed by a positron at x2 position. So here what happened is that this electron and positron, they met at x1 position, they annihilated at x1 position and turned into a photon, and this photon then produces a pair production. It creates a electron positron particle antiparticle pair, and they moved away like that. Okay, so that is what is happening here. We can call it as a prime b prime vertex. There are two vertices here as well, so it's a different kind of process but with similar incoming and outgoing products. Okay, and similarly the same photon is involved. You can see photon is involved. No, they are not similar. I'm not telling that. I'm saying that here it's photon and here it's photon as well. And we can see here that the both processes represent electron plus positron, virtual photon into electron plus positron. Okay, so these are the two Feynman diagrams for this process. This is the most crucial part in Feynman rules, to draw the Feynman diagram. It is to draw the Feynman diagrams. Now let's see what is the step 2. Step 2 is essentially to designate the momentum, to label the momentum to each of these particles so that the momentum conservation holds. So as I have already did it here, we'll do it for this diagram as well. So rule 2 or step 2 is to designate or label the momentum for each of these particles. Okay, we'll write it down, but let's do it for this one. Let's designate their momentums, and we will have u of 1 for this particle and p1 its momentum, and this is positron, so v bar of 2 second particle and p2 its momentum, then u bar of 3 as its wave function and p3 as its momentum, and we have v of 4 as its wave function and p4 as its momentum. Okay, in this way we have satisfied and followed two of the rules in Feynman rules. Let's write down the Feynman rule 2 so that we should have that idea that momentum labeling is also crucial and critical in here. Let's do that. And we'll refer to this diagram again and again, as I told you people that this is the foundation of all the calculations that we'll be doing later on. For each Feynman diagram, label the momentum of each line enforcing the momentum conservation at each vertex. All right, so here what does line mean? Here in Feynman notations, these are the lines you can see. We can also call them as external lines. Okay, these points are vertex, and this virtual and mediating particle that is emitted and absorbed by particles, the virtual particle that is involved in here, is called as propagator. It could be a photon, it could be a particle propagator, and it could be gluons, it depends. Okay, so we have a propagator in here. This particle, mediating particle, is called as propagator. We have these vertices where the momentum of the particles changes. Other than that, we have these external lines which we call as fermion lines if they are fermions. We can call them as boson lines if they are bosons, baryon lines if they are baryons, and so on. So these are kind of words or the names that we give to them, so they can appear frequently in the description part. Okay, so here they are telling us to designate the momentum of each of these lines. These are the curls. Okay, we can see this curly line. We don't need to designate the momentum of propagator. We just need to do it for the external lines, which are actually the incoming and outgoing particles, and the virtual particle is just involved in that interaction part, and that's it. So Here we can see that we need to do that. And note that one more thing to show here is that the arrows are only representing the incoming and or outgoing particles, and they doesn't tell us or they doesn't represent any information about momentum's magnitude or direction. What does that mean? If you are wondering that electron is moving in this direction, after interaction it is moving in this direction, this is false. Okay, these arrows are only telling us whether the particle is incoming or outgoing. For example, in most of the cases when you are given a Feynman diagram in exam, they will not tell you that which is the incoming particle and which is the outgoing particle. You have to determine and recognize yourself based on the knowledge from the Feynman rules, that which is the incoming particle and which is the outgoing particle. So incoming particle will move towards the vertex while the outgoing particle will move away from the vertex. And it is true for the particle part, it will be opposite for the anti-particle part. Okay, the anti-particle arrow will move away from the vertex, while for the outgoing will move towards the vertex. So this is how we determine whether the particle is incoming or outgoing, and whether this is particle. If they are straight lines, they are particle. If they are these curly lines, they are photons. If they are these springs, that shows they are gluons, and so on. So they are all representations that tell us that which particle we are referring to and what are they, whether they are incoming or outgoing. This is all they tell us. They never tell us that they are moving in this direction, they're moving this direction, like positons are moving in this direction. That's false. That is not what they are telling us about. Okay, so their momentum is p1, p2, p3 and p4. The magnitude could be different, they could be zero, they could be anything. We can't just say based on this diagram, and we are not even saying it. Okay, so these arrows are only telling you whether the particle is incoming or outgoing. They have nothing to do with the momentum's direction or the direction of motion. Okay, so keep that in mind. Don't confuse it and don't mix it. So this is the second rule. Now the third rule is to write down the amplitude function. And for writing down the amplitude function, there are three factors that we need to incorporate. As I told you people, that we have vertices, so there will be a vertex factor. Since the video has become lengthy, I'm uploading it in two parts. The next part is even more important, and I'll put the link in the description box. You can quickly go and check it out. Till then, take care and like, share, and subscribe.